Welcome to video 5.1 in our first Principles of Astrophotography series. In this video we discuss cameras and filters which are indispensable for astrophotography.
It's the big one. Remember that time when my photos came out blurry and you beat me over the head with my camera?
I never beat you over the head with your camera.
Well, yeah, I still have flashbacks.
Flashbacks or no, this video is based on section 5.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 75, sensor, into the meat of it. A camera sensor is a rectangular array of photosites that use the photoelectric effect to detect incoming photons by counting the electrons collected at each photosite.
So you got a little photosite, and this video 4.3 is where we introduced the photoelectric effect. We talked about Einstein's contribution. He got the Nobel Prize for it. It's where an incoming photon so there's two wavy line photons coming in. They hit a surface. They can, if they're energetic enough, they can kick electrons off of the surface. So these are electrons. And those electrons are collected at each photosite. The electrons have been kicked off. And that's how camera sensors detect light. That's how they measure it. And then they measure the number of electrons collected in the well.
Awesome. So that brings us to well capacity. The sensor well capacity is the maximum number of electrons that can be collected by each photosite.
So that's just the number of electrons you can put in that little well. That's all there is to it.
It's still important. 77, principle 77, bit depth. The sensor bit depth, N, is the number of bits used to store ADU values of the intensity, ranging from A equals 0 to A equals 2 to the N minus 1. This is really important. So we get the fine gradation between intensities of light.
Exactly. So for our sensor, it's a ZWO 6200 mm Pro. The bit depth, N, is 16. If you take 2 to the 16 power and you subtract 1, you get 65,535. And so the so-called ADU values, these are analog to digital units is what they're called, but they're really nothing more than just numbers between 0 and 65,535. So when you take a photo, you're going to get, for each pixel, a number between 0 for our sensor, and for most modern sensors, and most are 16-bit, you're going to get a number between 0 and 65,535. 0 meaning it didn't collect any light. 65,535 meaning it was probably saturated, probably received more photons than it could actually measure. And I want to go back on the well capacity too. For our sensor, the well capacity is 50,000 electrons. So each photosite on the sensor can collect up to 50,000 electrons. And you'll see for the smaller sensors, if you want to get a really, smaller pixels, smaller photosites, they can't collect as much electrons. And if you get these monster, so our pixel sizes are 3.76 microns, but you can get some sensors with 6 or 7 or 8 micron pixels, and they have huge well capacities.
Yeah, bigger.
And you just collect a lot of. But then the price you pay is you don't get as much resolution because you have smaller pixels.
Yeah.
So that's a trade-off you have to think about.
Yeah, with this camera, I think the FX30 that we're recording on, it's only 10-bit.
Yeah. Is that right?
Yeah, it's 10-bit camera. Yeah.
And I think the reason why a lot of astrophotography cameras have the higher bit depths is that we're recording these incredibly faint things. And you want to be able to get on the very, very low end of brightness, you want to get as many of those photons as you possibly can on the lower end.
Yeah. All right, pixel size. The pixel size P of a sensor is the width of one of its photosites measured in microns. We already talked about.
Just as we talked about. So capital P we use in the book to describe the pixel size. And those are measured in microns. 1 micron, it's denoted by, this is the Greek letter mu. And this is just a good old-fashioned M. And this means 1 micron. And that's 10 to the minus 6 meters. So that's 1/1,000,000th of a meter. 1/1000th of a millimeter.
Right.
So these are really small. The width of a human hair is about 100 microns. So we're talking about fitting 30 of these pixels, of our pixels on our camera, across the width of a human hair. Yeah, the technology, I don't know, it just blows my mind. Back when I was young, astrophotographers were developing film. And, you know, on these emulsions and things, yeah, it's just amazing what's happening today. So that's just the width of one of its photosites. Also, I've heard of, I've never actually seen, but some sensors will have a different width in the Y direction than it is in the X direction, but almost all cameras nowadays just have square pixels. They're the same width as
Makes
as
sense.
height. Yeah. There's really no reason to prefer one direction over another one.
Yeah.
Yeah, so that's it for pixel size. It's just the width measured in microns. The C-Star, I think, has a pixel size of 2.9 microns, and which is on the smaller side for sure.
Yeah. Principle 79, sensor pixel dimensions. The dimensions of a sensor give its length and width in pixels, and their product, n equals length times width, gives the total number of pixels.
So for our camera, you can do the same with your camera. The number of pixels in the horizontal direction is 9,576. It's a full frame camera. And in the vertical direction is 6,388. If you want to know how many pixels are on that sensor, you multiply the length by the width in pixels, and you get 61 million pixels on our sensor. That's what they mean when people talk about a 61 megapixel camera. It's just this number, multiplying the length by the width. There's nothing fancy there. Yeah, that's it on that one.
Easy. Principle 80, sensor linear dimensions. The linear dimensions of a sensor are given by multiplying its pixel dimensions, length times width, by its pixel size, p, and dividing by 1,000.
So why the 1,000? So we're asking now about the linear dimensions of a sensor, meaning, and you might have noticed we should have had a sensor here to take a pic to let you look at, but the sensor is just a little window, and how far across is it in the horizontal and the vertical directions? That's what we're talking about here, the linear dimensions. And to find it, as you might well have guessed, you just take the pixel size, 3.76 microns, you multiply by the number of pixels in the horizontal direction, and that'll give the width. But that'll give you a width in microns. And usually these widths are measured in millimeters instead of microns. And so if you divide by 1,000, then you'll convert the microns into millimeters. So if you do that calculation for our particular sensor, multiply L by P, this L by this P, and then divide by 1,000, you get 36 millimeters in the horizontal direction. And then you do the same in the vertical direction, and you get 24 millimeters, or something close to that. That's how you figure those linear dimensions out. But these linear dimensions are important because that tells you I mean, if the object you're trying to shoot goes outside those limits, then it's going to be clipped off. It's not going to be completely in the field of view. So we have a bunch of videos that talk about that too.
Principle 81, bandpass filter. Color astrophotography relies on bandpass filters placed between the telescope optics and the camera sensor. These filters pass a range of photon wavelengths called the pass band and block the rest.
So for example, here is a chroma green bandpass filter. And we'll talk about this in just a second. The transmittance is the fraction of the incoming light that's actually that passes through the filter and gets to your sensor. And the fraction, or the percentage. So as you can see, these are very, very highly regarded filters. And when our ship comes in someday, maybe we'll have chroma filters. But we admire the people that do have them. And
buy the book.
Yeah, yeah. Please buy a copy of our book so we can buy some chroma filters. But they are kind of, at least right now, kind of the holy grail of filters, but they're very expensive. Well, they say that astrophotography makes millionaires out of billionaires, but unfortunately we did not start off as billionaires or millionaires. So this right here, between here and here, are the range of wavelengths that pass through the filter, and then all the other wavelengths are excluded. That's the whole idea.
Principle 82, transmittance. The transmittance of a filter is the fraction or portion of incident light that is transmitted through the filter as a function of wavelength.
Or the percentage.
Or percentage, right.
Like we talked about there, yeah.
Yeah. Principle 83, bandwidth. The bandwidth delta lambda of a filter is the full width at half the maximum transmittance.
So it's the old full width at half max, and we'll spend a lot of time thinking about full widths at half maxes for stars and that sort of thing, but the same thing applies here. So delta lambda is at half the maximum, so here's the maximum here. It's almost 100%. If you take half of that, and then you measure the width of that pass band at half the maximum, that's called the bandwidth.
Principle 84, one-shot color camera. One-shot color cameras have a built-in filter layer that covers the sensor in a Bayer pattern of tiny colored filters, each covering a single photo site. And I can just imagine this guy with tweezers putting the little filters on to the little photo sites.
Yeah, and some people, I've heard of people, they're just a little layer of dye or paint or something they put on there. And I've heard of people who want to turn their color camera into a monochrome camera, just taking a knife and scraping it off.
Ah, cool.
I wouldn't dare scrape off my sensor. I mean, they worry to death about scratching that sensor or something like that. But Ren and I, when we first got into the hobby, we didn't know how you get color images, and we wondered whether the camera sensor elements can tell what the wavelength of the photons that are coming in. The photo sites cannot tell what color of light is hitting them. All they can tell is they got hit by a photon. That's it. And so in order to get a color image, you have to put a filter in front of the photo site. And we'll talk about other forms, but most of your camera, I mean, can't imagine any of your phones that you have or your cameras that you have would not be one-shot color cameras. I think most phones are one-shot color camera, right? Yeah.
Yeah, no, they're all one-shot color. And if you want an excuse to go mono, the fact that each one of these photo sites is covered by a filter, green twice, the fact that you get 4 times the amount of resolution when you go mono than when you have color camera, because each one of the photo sites is not just being used for red, green, blue, red, green, green, or blue, or red, blue, red, whatever the Bayer pattern is. but you're counting every single one of those sites in a monochrome. It's high resolution right off the bat for free.
Yeah. So in a one-shot color camera, this is right here. That's the pixel size, P. So that's 1 pixel. So that first pixel in the pattern has a red filter over it. So it's only going to detect red photons. And then this next one next to it is going to detect green, etc. So what Ren was pointing out is that you don't, for this green pixel here, you don't get any information about red or blue. All you have is green.
Right.
And so that does affect the resolution, and we'll talk a little bit more about that.
But blue is only counted every 4th pixel.
That's right.
So you're only getting blue on 1/4 of the number of
the total pixels
that you have on your camera.
So you don't have, and so what happens is that after you take that picture, then there's a process called debayering, where you interpolate the color. You interpolate an R value and a G value and a B value for each photo site in the sensor.
Mm-hmm.
This pixel, you don't have to interpolate the red. You already know what the red is.
Right.
But if you want a value of green for that top left pixel, then you have to say, okay, well this pixel, this green pixel measured a certain ADU value, and then the one over here, and then you have to interpolate between them. So it's a lossy type of thing. It's not a perfect system. You're just doing the best you can to try and recover the value of R, G, and B for each pixel. Also, and a lot of amazing astrophotographs. We're not dissing the one-shot color cameras. There's advantages and disadvantages to both. One-shot color is just really convenient.
Oh, man.
You don't have to worry about filters or anything. You just take the pictures and you process them and you have a happy day.
Principle 85, monochrome camera. Monochrome cameras rely on removable glass or quartz filters in the optical train to select the pass band for the entire sensor.
Okay, so you're in a monochrome camera, there aren't any filters placed over all
The individual
over the individual
photo
pixels.
sites, yeah.
So you're going to put, say, for example, a red filter over the whole thing, and then while you're shooting with that red filter, you're going to capture the red photons for all of the pixels. Then you're going to put a blue filter in front of it, and then you're going to put a green filter in front of it. And then in post-processing, you have 3 monochrome images, one measuring the amount of red in each pixel, one measuring the amount of blue, and in post-processing, you combine those together to form a color image.
So, quiz question here.
Okay.
Why in like sports photography don't we use mono?
Well, because the subject is moving,
Yeah.
right?
Right. So this only works
If
for
the subject is holding
stationary,
still.
perfectly still subjects. Yeah.
Yeah. Well, that's a great question.
Thank you.
You
passed.
Thank you.
Yeah.
Awesome. So these filters, these glass or quartz filters, can be on the pricey side, but my impression is that these filters are of higher quality than the little dyes that are placed over the RGB sites. Yeah. For example, a lot of them, and we'll talk later in this chapter, in future videos for this chapter about narrowband filters, and those are interference filters where tiny thin layers of dielectric materials are placed on there in order to create like an almost perfect bandpass situation, like the green that we showed for chroma. Thanks so much for watching.
And we'll see you next time.